from Rice University to visit us here. So Dr. Huang is chair professor in physics and astronomy in Rice University. He is actually alumni of our physics department in 1962, and he became our distinguished NTU alumni in 2 years ago, 2012. So he got his PhD from Cornell, and his research mainly focused on membrane biophysics, as you can see here from his title. He received a Venti Award for Lipids from Biophysical Society. Also in 2012, he published many papers in Biophysical Journal, which is, I would say, the most distinguished journal in the field of biophysics. So please join me to welcome Dr. Huang here.
Let me first thank Professor Su Siwei 教授给我这个机会跟各位见面。My talk today is about. Is it on?
Can you hear me?
Hello.
Can you hear?
I don't think it's on.
Yeah, I also don't think it's on.
So how do I turn it on?
It looks to be on now. But okay.
Is it on? Is it on?
No, not really.
It's on. Is it better? Better? Yes? No?
No. Or try this.
Okay.
Sorry for the inconvenience.
No problem. Okay. Can you hear me now? Yes. Okay, my talk today is about proteins which are designed to work with cell membrane. And you see that what I'm going to talk about are physical process, because in biology you can have either chemical reactions or complicated processes. I want to emphasize what I'm talking about is really physics. I know the audience. No chemical reactions, and you'll see that the functions are very well defined, even though it's in a material which you all are not familiar with. And in fact, the processes will be described as phase transition. And at the end of the talk, I'll mention some interesting related programs which are unsolved, so that maybe you can think about. Okay, the subject of my talk is new kind of antibiotics. These antibiotics are going to work on membrane. I'll explain what is the significance of it. And this kind of, there's a name for this kind of antibiotics. It's called antimicrobial peptide. And the talk today is a story of how we solve this problem. I'm sure all of us have experience of using antibiotics, right? You get infections, you take antibiotics, and the problem solved. We often forget how important it is, the discovery of antibiotics to the history of human beings. Before the discovery of antibiotics, penicillin being the first one, people often die of infection from injury, from pneumonia, from all kinds of diseases. And if you read the history, most families have children die before they reach adulthood. Many mothers die from childbirth. Very, very common. But all of this miseries stopped when antibiotics were discovered. Antibiotics work with a very, very simple principle. Because microorganisms, bacteria, fungi, all kinds of pathogens, they always compete with each other for food, for space. So evolutionary, almost every antibiotic or microorganism will produce something, a small chemical compound, which would attach to a protein on the surface of bacteria. And proteins, your physics student, you probably don't know, are basically chemical catalysts. All proteins are controlling some chemical reactions in the cell. So if the antibiotics interact, an important protein catalyst, antibiotics just stop growing or just don't grow well, and that's basically how antibiotics work. But bacteria, by evolution, were designed to mutate. So they often have one mutation which will make the protein target of antibiotics don't bind that antibiotics. And when that happens, because antibiotics kill off all the bacteria except this one, this mutated bacteria would soon take over all the space and eat all the food and grow exponentially until a new antibiotic is formed to kill that bacteria. And this has been the cycle ever since the discovery of antibiotics. We don't know it, but that's what's going on. Until 20, 30 years ago, nobody cared about antibiotics because, if you're sick, you just have to take antibiotic, problem solved. Every doctor looked like a good doctor. All the give you a prescription of antibiotics. But about 20 or 30 years ago, people begin to misuse or abuse antibiotics. They use it to grow chicken, to grow cows, and every time you feel sick, you get antibiotics. That's the abuse. A lot of time you don't need it, but you take it anyway. Well, then you increase the chance of bacteria to mutate, to resist antibiotics. And you have read in newspapers that there are bacteria in hospital resist to all the antibiotics. And if the patient unfortunately catches kind of super bug, they resist to all antibiotics. There's no cure. So the discovery of a new kind of antibiotics is a big deal. And this happened about 20, 30 years ago, 1980s, that there's a new kind of antibiotics act on membrane rather than on protein. I'll explain a little more very soon. So, and this kind of antibiotic actually is very common again. Not only microorganisms have this new kind of antibiotics, every animal, plants produce this kind of new kind of antibiotics. Human produce it. Where do you find it? Within the white blood cell. When white blood cell capture bacteria, that's how white blood cell kill bacteria inside the cell. And you all know that our big intestine has a lot of bacteria, right? Our small intestine is clean, no bacteria. How can you achieve that? Because on the boundary, we produce this kind of bacteria to kill off any bacteria come to the small intestine. So it's very desirable to make use of this new kind of antibiotics, a drug. But that has not happened because we don't, for a long time we don't know how it works. You don't know the mechanism. So it did not achieve the FDA Food and Drug Administration approval. So these are, although this is a common antibiotics, has not been approved as drug. But I want to tell you how they work. So, let's see, let's go back. And so I have explained the significance of this new kind of antibiotics. And in a few slides, I'll explain what is the problem we will try to solve. And like I said, near the end, I'll tell you some related problem which is unsolved. So I'm going to tell you the solved problem, but I'll mention some unsolved problem, very much related. So I was telling you that these antibiotics work on cell membrane. And how does cell membrane look like? Well, this is the actual microscope of best image of antibiotic of cell membrane. You probably cannot have any higher resolution than this. And you can see that it's a double layer, and the structure of this cell membrane looks something like this. There's a double layer of something called lipid bilayer, made of one layer of lipid molecule, another layer of lipid bilayer called lipid bilayer, and on which you have a lot of this blue stuff. This is a cartoon for proteins. The conventional antibiotics which have been using, we have been using, you have been using, are the antibiotics that would attack these proteins. The new kind of antibiotics attack this lipid bilayer. So they work with very different mechanisms. So the resistance to the antibiotic, to conventional antibiotic, is mutation of the protein. It's very difficult for bacteria to mutate the membrane. So this new kind of antibiotic actually has no resistance. This is a cartoon. You know, if you open a biology textbook, you see this cartoon. But this is just a cartoon. We don't know if cell membrane really look like this. We don't, actually. So we want to study how antibiotics interact with bacteria membrane. So we try to produce bacterial membrane to do experiment. How do you do that? Bacteria small. This is the most common bacteria, E. coli. It's about 1 micron in size. And so it's difficult to study it even under a microscope. You can use conventional antibiotic to make it stop division so that this E. coli becomes raw. It's a cylindrical kind of thing. And why is it? Because outside of its cell membrane, there's another layer of membrane called outer membrane. And in between, there are some polymers make the shape of bacteria cylindrical. If you use some kind of chemical enzyme to digest the external membrane, it will become swirl. Now this time, this goes 3 plus, it's still alive, same bacteria, but no outer membrane, so it's spherical. And you can make it larger by play with osmolarity of the solution. Question? No. Okay, so we want to study how antibiotics interact with the cell.
How do we know it's still alive?
Because you can put it back. In fact, if you give them nutrition, it will grow back to this.
Okay.
Yeah.
So will it go under mitosis?
Yeah, you will grow back.
Okay, good.
Yeah. They don't divide, but they'll grow back.
Go back.
Yeah. So, but then, you want to study how antibiotics interact with the membrane. But how do you study? What do we want to measure? Well, you all know condensed matter, right? You want to study condensed matter. Usually, you want to see the electronic properties, right? So you do photo emission, electrical property, magnetism. You know what to measure. But what do you measure of the cell membrane to study what's going on? This is the question. When a physicist is going to membrane, any biological system, the first question you're facing is, what do you measure? So we thought that, well, why don't we measure the energy of membrane? So energy per unit area is tension, right? So we study tension. How do you study tension? This is the bacteria. You use small glass tube called micropipette and apply a little negative pressure to make the sphere into a sphere plus a cylinder. Why? Well, if you don't do that, if there's a small change of area, it's very difficult to measure because the change of radius is so little. It's very difficult to measure the membrane area change. But if you do this, there is a difference between the area volume ratio of sphere and the cylinder. So if there's an area change, the volume does not change because the osmotic pressure keeps the volume constant. If there's an area change, then the portion of sphere and cylinder will change. And that is very, very obviously seen if you do this. So you do this experiment so that if there's an area change, you can easily measure. So, for example, if you apply tension, the area will increase. And you can, this is an experiment done on this E. coli sphere plus. And you can increase, and decrease. It's totally reproducible, reversible. But so you think that cell membrane is like elastic material. Well, it is, but maybe not. See, if you change the tension from here to here, area will increase. But it takes 100 or 150 seconds to reach new equilibrium. Now, if you stretch a rubber band, the speed of change is controlled by speed of sound. So it's almost instantaneously pull it expands. This takes 100 seconds to expand to the new volume. You pull again, another 100 seconds. If you go back, take another 100 seconds to go back. But it's totally reproducible. Very strange. Cell membrane is, often people think that it's just a piece of material like a rubber band. It is, but it's not. And it's stacked. How do you know it's stacked? Well, you see that everything goes out. It got empty. The membrane is still there. You can still pull. And again, the area increases tension, but it doesn't go back. So it's what I'm trying to tell you is difficult to do an experiment with live membrane. Well, this is when we put this bacteria here, and we put the antibiotics outside in the solution. And they will bind to the membrane, attack it. We want to know what's going to happen. We put some dye molecule outside just to see if they will leak into the cell or not. We put red and green. Red goes in. Green did not go in. And red come up and green go in. It's very complicated. So the live cell is very difficult to do physics experiment. You don't know what's going on. So what do? We make artificial membrane. Physicists always simplify things. You have to remember you have simplified things. So this is not the same as a real system. Nevertheless, that seems to be the only way you can find out what's going on. The artificial membrane is easily done. You buy something called lipid molecule. Lipid molecule has one part soluble in water. One part is oily, so it doesn't want to be with water. It's called hydrophobic, hydrophilic. You dump into water, it spontaneously forms lipid bilayer. So to hide this hydrophobic from the hydrophilic surface, and you don't want this system doesn't want this part to be exposed to water, so they form a film. This is automatic. You don't need to do anything. You just shake lipid molecule model, it automatically do this. And we think that that's how life started long time ago. That you want to make a cell, you have to have some boundary to enclose the reactive material to make a cell, right? So that's how things started in biology. So what we want to start is this artificial lipid bilayer in this form. And what about the antibiotics? Well, like I said, every animal, every plant, every microorganism produce this kind of antibiotics, which are all different from one animal to another, but they're all very similar. They work the same way. That's almost a proof that it's not chemical, because they are all different. But they're all similar in the way that the size is about the same. And so one, for example, it's like a helix, like a helical protein. And one side is the chemical composition on the surface is hydrophilic. The other side is hydrophobic. So this kind of thing is like a detergent. Detergent, that's how it's done. The detergent when you wash something, you have one side hydrophobic, other hydrophobic, so that you surround the oil drop to make it dissolvable. So this kind of thing is going to interact with lipid barrier because lipid barrier has a hydrophilic, hydrophobic interface. And this also has hydrophilic, hydrophobic interface. So they would naturally bind to each other. So the question is, what's going to happen if membrane exposed to this? Okay, sounds like a very simple problem, right? So what do? We take this artificial membrane and did the same thing again, use micropipette to measure the area change. When antibiotics, which with a green dye so that it's visible, is in the solution here. And why is red? Because I put the red dye inside, so that if there is leak, you can see the red dye comes out. Okay? Now, so, oops. What happened? I don't know what. Yeah, I want to play. Yeah. Okay. So you see that. Oops. Oh, that's all we have to do. Okay. So you see that the green it's becoming green because the antibiotics attached to it, and the membrane would increase, and then you see that the red dye leak out. Okay, it's again green dye attached to it, membrane increase area, and then at one point this stuff just leak out. So if you look at the data, what happened is that the green surface of the membrane, the green intensity increased linearly with time because they bind to the surface, and the red symbol area change. And area change is proportional to amount, which makes all the sense, right? It binds to the membrane, increase the interfacial area, so the volume increase. But what's interesting is that at one point, when the area change increased 4%, about 4%, it leaks out. We repeat this experiment with different vesicles, different preparation every time. When the membrane area increased about 4%, 3.5, something like that, it leaks out. So it looked like these antibiotics make holes in the membrane, even though membrane seems to be intact. So we want to see if there are really holes in it, okay? So let's imagine that there are holes. How to detect the hole? We take this vesicle, lipid vesicle with antibiotics on there, probably making hole in the surface, remove most of the water. The lipid molecule is such that they will automatically become self-prime. This is called symmetric liquid crystal. It's just the nature of this kind of molecule. You don't need any effort at all. They just spontaneously remove them, just evaporate, it will become like this by itself. If you look under the microscope with polarized light, you see this shiny light. Why? Because this kind of liquid crystal, symmetric liquid crystal, has a low energy excitation called oily streak like this, which is birefringent. That's why you see this shiny light. And you can massage the sample to make this line goes away. You take this layer to the neutron source, and let the neutron hit it perpendicular to it. You can then tilt the membrane and move the detector to catch the diffraction pattern. I'll only talk about in-plane scattering when the planes are perpendicular to the membrane. This